Thanks for attending today's Macrone Group webinar. My name is Charles Zona, and today we welcome Glenn Miller and Jeff McGinn from Macrone Microscopes and Accessories. Glenn and Jeff are going to talk to us today about choosing the right microscope through a multi-tiered approach when it comes to the analysis of bandages and wound care products. They will discuss the use of the latest benchtop SEM technology and stereo microscope, along with the Linkam Modular 4-stage as they relate to specialized wound care products on the market today. You can ask questions by typing them into the questions field, and we will answer all of your questions individually in the coming days. Also, a recording of this webinar will be available on the Macrone Group website under the Resources tab. And now, I will hand the program over to Glenn and Jeff.
Thank you, Chuck, and good afternoon, everyone. This is Jeff McGinn, and I'm joined by Glenn Miller, and as Chuck mentioned, we are going to discuss a multi-tiered microscopy analysis approach on some of the latest bandages and wound care products on the market today. Wound care products make up nearly a $20 billion global market. And over the years, we've seen many improvements in the ways that they function and promote healing. They now come in a variety of shapes and sizes and provide protection through features like waterproof technology, flexibility, and tough, resilient coverings. Now, as microscopists, we may consider ways in which to analyze them. And we might view them under an optical microscope, a scanning electron microscope, or both. We might be interested in things like the thickness of our product. Is it multi-layered? What about its elemental composition? If a product is marketed as flexible, you'll certainly want to determine its tensile strength. So, much like we do in our own laboratory, a multi-tiered approach is sometimes the best course of action when we're doing any sort of investigational analysis. And many of our clients also operate their own labs in this manner. And certainly the thousands of students that we have taught over the years use more than one instrument to accomplish their goals. So today we'll use three instruments: a JUL benchtop scanning electron microscope, a Nikon stereo microscope, and a Linkam Modular 4-stage for tensile strength testing. So let's analyze two different types of wound care products. One promoted as maximum hold waterproof, and the other heavy-duty strong strips. We'll start with the benchtop scanning electron microscope. The JUL JCM 7000 is a benchtop SEM capable of 100,000 times magnification, 8 nanometers resolution, and appropriate for a wide range of samples, including both conductive and non-conductive type specimens. It's a fully automated system and includes a high-powered tungsten electron source. All right, so here's our live image with our two samples, our heavy-duty strong strip there on the top, and down below our maximum hold waterproof bandage product, both mounted flat as well as vertically so we can see those cross sections. So I'm going to go ahead and click on my optical image and zoom in to where I get to the electron image, and click on my sample. It moves the stage automatically. I can slow down my scan rate to a slower scan to sharpen up my live image. It's got some nice auto features: auto focus, auto stigmation, and auto contrast and brightness. And I'll go ahead and give this an auto focus. and I'll wait for this live image to sharpen up. You can clearly see the distinct layers within this sample. Over on my right is my live EDS showing elements present. Looks like carbon, oxygen, and silicon. And I'll go ahead and click off of this. I'll speed up my scan rate for a little more real-time movement on my live image, and I'll go ahead and just investigate what this surface looks like on the top of the bandage. So I'll go ahead to some random area, slow down my scan rate, and I'll give it another auto, this time an autofocus, auto stigmation, and auto contrast and brightness. And I'll wait for that to come into play, and there it goes. And I got a nice, crisp, sharp backscattered image. I'm looking at a backscattered image right now of these samples. And down below you see my signal, backscatter, magnification, accelerating voltage, working distance, probe current, my vacuum mode, and the counts per second that are hitting my EDS detector, again my live EDS on the side there. So I might have an interest in doing a little more analysis on this cross section here of my heavy duty strong strip, and I'll go ahead and navigate to that area with my automated stage and zoom in, and as before I'll want to slow down my scan rate. I'll go to a slow scan and give it a quick auto, an autofocus, an auto stigmation, and an auto contrast and brightness. I can clearly see distinct layers within this cross section. That top layer, that bright one, is the area that comes in contact with your skin. There's a middle adhesive layer, and then there's the fibrous top layer, which is actually at the bottom of this live image. But within the software, there's a nice ruler measurement function. Right click on that, and I can do a point-to-point line measurement, quick and easy, about 142 microns there. And then this top layer, you're looking at about 80 microns. Okay, so let's go ahead and take a look at our second sample, the waterproof bandage, and we'll go ahead and we'll zoom in on the cross section of that, and as before we'll slow down our scan rate, and let's give it a quick auto, an autofocus and auto stigmation and contrast and brightness. And we'll look at some of the differences in this sample. And now it'll come into focus. The waterproof film is actually at the lower portion down here of the sample. So I'm interested in that area, so I'll investigate that layer. Again, this is a BSE or backscatter compositional image. It basically means a backscattered electron image which exhibits the difference in the average atomic number in a specimen. So I'll give this another autofocus. And something like this, I'm interested in some of these brighter areas, darker areas, anything where I might see contrast. And within those areas, I might be interested in obtaining a quick EDS spectrum, noting differences in elemental composition. And we can see there are some areas that are noticeably brighter within that layer. And just to investigate, I may want to click on some of those areas. My live EDS shows carbon and oxygen, but let's go to element analysis. And I'll go ahead and I'll choose select mode, and I'll go back and I'll click on an area within that thin film that's brighter, and I'll go ahead and I'll just click it. And that immediately on the right hand side there gives me a strong silicon peak. Looks like there was some aluminum present. And then I might do the same with other areas. So clicking on that, I see some chlorine, and you get the idea. All right, so let's navigate down to this other area on the waterproof product, and I'll go down to this brighter area, which I suspect is the paper backing. As before, I'll slow down my scan rate. I'll go through some of the auto functionality and let this come into a better focus. And take a look, and yeah, that's exactly what it looks like. It really pops under this charge reduction vacuum. My live EDS is showing noticeably different elements, a high silicon peak. There's my waterproof layer, paper backing on the right side. I'll zoom in on this a little bit, move my stage, and slow down my scan rate, give it another quick auto. As we wait for this to come into focus, I'd like to mention that we've recently filmed our very popular SEM class, and we'll soon be offering it in an online format. Watch for that in the next few weeks. Be likely a 2 to 3 day SEM class loaded with valuable information. And this comes into focus. And as I mentioned earlier, my live EDS is showing different elements now. I'm seeing some calcium in there. And again, that high silicon peak from the paper backing. Let's do one more quick analysis on this heavy-duty strong strip. Let's do a quick EDS analysis, say on an entire area of this cross-section. And we'll go ahead and we'll give it an autofocus as before and wait for that to sharpen up. And from there we'll go up to our purpose 1, and we'll choose element analysis and go to placement mode over on the right, and I can draw an area within the sample, and I'll just draw a box, and I'll go ahead and I'll hit start, and the system will automatically go into this scan EDS mode. So periodic table appears. It looks like I've got about 32 seconds left on this analysis. It's an area. It's showing my elements present, my periodic table up top, which are being auto-identified. I can manually identify elements if I wish. I can disable elements. So if I want to rule out things like carbon, I can do that. And we're almost done here. We've got about 3 seconds left. And it will go ahead and finish and put it into this data management folder here on the left. And I open that up and find the spectra that I just generated. Go ahead and click yes and open that up. And there's my image, my area, my detected elements. I can drag out this spectrum and sort of get a better idea there. There's a nice quantitative result feature there, and I can send all of this to a quick report, and it'll take all of my information, the spectrum, the image, my optical image, and all that data, my quant data there on the right, accelerating voltage, magnification, and it'll put that all into a nice report for me. Okay, so we've looked at our 2 samples under the SEM, and we may be interested in in learning a little more about their properties. And in this case, since these bandages are marketed as flexible and waterproof, we have the opportunity to also measure their tensile strength. So for the next few minutes, our Macrone technical sales representative, Glenn Miller, will spend some time looking at them under the Nikon stereo microscope and the Linkam modular force stage. So with that, I'll turn it over to Glenn.
Thanks for the introduction, Jeff. Hello everyone, my name is Glenn Miller and I'm a technical sales representative at Macrone Microscopes and Accessories. Today I will be talking to you about our further investigation into the tensile properties of these two wound care products. I utilized a Nikon stereo microscope and the Linkam modular force stage to conduct these tests. To dive a bit deeper into the Linkam modular force stage, there are several options on how to configure this system depending on the sample type that you have, as well as what you want to achieve in your testing. These options include different heater bases, ranging from liquid nitrogen temperature up to 350 C, electrical connections, different grips, and different beams. All of these options can easily be removed and replaced depending on what testing you would like to conduct. In order to analyze these two wound care products consistently, I tried my best to cut out similar sized sections of each bandage, as you can see below. These bandages were then mounted in the modular force stage using the same grips and the same 200 Newton force beam. I plan to run similar tests for each of these bandages, including 2 sets of cycle stretches and 1 full stretch to try and determine the maximum breaking point for each bandage. For this testing, we did not include any heating or cooling, but just stretching. The first test was for the waterproof bandage, utilizing a cycle stretch of roughly 2.5 millimeters at 0.63x magnification. What I noticed was that the brown dotted layer of the bandage tore apart quite easily after the first cycle. On the graph to the right, you can see the blue line indicating the extension amount over time, and the yellow force line below gradually decreasing at maximum extension as the cycles went on. The second test for the waterproof bandage was similar to the first, utilizing a cycle stretch, except this time going a bit further to roughly 4.5 millimeters. I noticed a large force required for the initial stretch, and then the stretches afterwards required less and less force, indicating that elasticity of the bandage was not maintained as well as in the first cycle test. The third test for the waterproof bandage was the full stretch test. I started this stretch at roughly 20 millimeters distance and ended at roughly 70 millimeters of distance, covering a full 50 millimeter of stretching distance. About 55 newtons of force was required to achieve the breaking point of this bandage, but it did not completely tear apart. There was a clear layer that stretched the most and stayed together through the entire test. The first test for the heavy-duty bandage was the same 2.5 millimeter cycle that we did for the waterproof bandage, and we saw similar results. The force dropped gradually as cycles went on, but it seemed that the woven pattern of this bandage allowed for more elasticity and it maintained its force better than the waterproof bandage. The second test for the heavy-duty bandage was the same 4.5 millimeter cycle that we did for the waterproof bandage, and once again results were similar. There was a large force required for the initial stretch, and it seemed to reach a breaking point, which led to much less force being required for subsequent stretches. For the initial stretch, it required a full 90 newtons of force, and then for stretches afterwards, it only required roughly 20 newtons of force. The final test that we did for the heavy-duty bandage was another full stretch. We saw slightly different results for this bandage, as there was 150 newtons required to reach the initial breaking point, and then it seemed that there was a secondary breaking point around 60 newtons of force. This could have been from the woven material being tangled in itself after the initial tear, but overall we saw much more force required to reach that initial breaking point with this bandage. All in all, we were able to conduct successful testing on these two bandages and capture some interesting data. For the waterproof bandage, it had a breaking point of roughly 55 Newton, and the brown layer of the bandage seemed to tear apart quite easily even in the smaller cycle stretches. But the plastic waterproof layer of this bandage was very tough to tear in all of the stretches. For the heavy-duty bandage, it had a breaking point of roughly 150 Newton in the full stretch, and the woven materials of the bandage seemed to allow for more durability and strength throughout shorter cycle stretches and the full stretch. So we can then furthermore use this data combined with the SEM data to give a more all-around analysis of these two types of bandages.
Thanks to all of you who tuned in today. We really appreciate your time. Please check out our webinars page for other webinar recordings and for upcoming Macrone Group webinars. Thank you.